The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I'm going to talk about alternate consensus mechanisms. And there's a bunch of them. And sort of some of them are variants on proof of work, some of them are proof of stake, all these different things. So unique node lists, this is something that Ripple and Stellar use. I'm not sure if there's others. Proof of stake is like this huge research topic that lots of things fall under. There's lots of variants. One of them I'll talk about is delegated proof of stake. Proof of space is an interesting thing that is basically a form of proof of work that doesn't use CPU as much. There's the idea of directed acyclic graphs, which IOTA is a great example of. And then one that I sort of came up with a few years ago and is kind of fun, proof of idle, which is sort of silly, but some of these others are silly too. So, okay, and so sort of disclaimer. I'm okay with proof of work. So like I think if you were at the class on Monday, it's a great sort of segue into this, where clearly proof of work has, I don't know if you want to call it problems, but like it's kind of crazy, right? All the stuff David was saying on Monday, it's not an egalitarian, you know, and I think in the Satoshi white paper he sort of says one CPU, one vote. Well, that's not really how it works. There's even if you define CPU, maybe you have your own CPU, someone else has a different CPU. And there's that huge industry of building all these chips. So there's a lot of issues with proof of work. It's certainly not ideal. That's probably not why most people don't like it. So I generally, in academia, in a lot of business places, people don't like the Bitcoin proof of work mechanism. Not everyone, but it's a pretty widespread like, oh, Bitcoin is bad because it uses as much electricity as Denmark or something. And I think that's a sort of early, I don't like it because it uses electricity. There's other reasons not to like it, which I think you have to go into much more depth, like with David's talk yesterday. Sure, it uses a lot of electricity, but it also uses a lot of fabrication plants. And it uses all these other sort of distribution networks. So anyway, I get that there's a lot of, one of the first things with Bitcoin is, okay, how can we improve upon this? How can we get rid of this huge energy sink? On the other hand, I'm sort of okay with it, right? Like I've been, the first thing that I thought about Bitcoin is, wow, this is going to be huge. This is going to take a lot of electricity, but it's kind of cool that it works that way. So I'm sort of okay with people, if like, to me, like you can't really get mad at people doing things you think are stupid because you'll just get mad all the time. Like people mine gold, people spend billions of dollars on diamonds. I think diamonds are really stupid. But hey, if you want to dig up diamonds and whatever. Yeah, there's entire cultural areas that I just have no interest in, but hey. Okay, so I'll try to explain these other methods in a neutral way, but I do have my own sort of biases where I think like, hey, proof of work pretty much works. I think it's a cool system. And I'm somewhat skeptical of various different algorithms and mechanisms here. And so I'm most familiar with the proof of work system and all the sort of intricacies of it. So like with David's talk yesterday, like there's some new stuff, but I sort of knew because I've talked to these people for a long time and like this is how this system works. Proof of stake, I've seen it implemented in altcoins, but I haven't followed them that closely. So I don't know as intimately like what goes wrong and all the weird details. But anyway, okay, so the first one, UNL, or unique node list. This is essentially the consensus mechanism used by Ripple and Stellar. For history, Ripple started 2013, 2011? I don't know. It was a while ago.
Genesis, January 1st, 2013.
2013, okay. But so actually the Ripple, the name Ripple and the idea of sort of these debt obligations through this network was actually predates Bitcoin. And then Jed McCaleb started the company. He's also the guy who started Mt. Gox. So he started Mt. Gox. I believe in 2011 or late 2010. Sold it to Mark Karpelez, started Ripple, hired a bunch of people, sort of got fired from Ripple. A lot of everyone fighting, because like, it was all these people who used to play Magic the Gathering and like were friends, and now they're not friends anymore, and it sucks. And then he started Stellar, which he called Secret Bitcoin Project. And I was thinking of joining it, but he wouldn't tell me what it was. Also it was like, I knew that other people knew what it was, like my friends, and if they weren't telling me, because they're not supposed to, it was like, well, it must not be that cool, because nobody can actually keep a secret if it's really cool. So that was my sort of like, I'll just go work somewhere else. And Stellar was more or less a copy of the Ripple code, which was open source, so it was totally fine to do this. And then it sort of diverged, and they added their own sort of different parts of the consensus algorithm than Ripple did. So it's account-based, somewhat like Ethereum. Transactions have sort of senders, receivers. What's interesting is in the Stellar case, and possibly Ripple, there's a minimum balance. So I actually had some Stellar last year, up until last year, because I went to the sort of initial release party, and they gave out Stellar. And I had some, and it was like, then it wasn't much, but then last year I looked and it was like, oh, this is like $200 worth. I'll sell it, and I sold it. Got some Bitcoins. But it was weird because they enforced a minimum balance, which seemed like weird to me, because you had to retain some number of Stellar units in every account, which to me seemed like sort of weird, because that means like those Stellars haven't really, they're sort of gone in a way, in that if you open a new account and it must have 50 Stellar in it forever, well, those Stellar are effectively destroyed. It just seemed like, I mean, which is a fine thing to do. It's sort of a transaction fee, but from a computer science like database standpoint, it's like, why not just have it cost money to create a new account instead of have a minimum balance? I don't know. So these are sort of just interacting with it. It's like, so there's no work, but the idea is that nodes sign transactions that they've seen. Everyone sort of makes blocks, and you sign them. So you've got some kind of identity. Your node has a key. When you start a new node, you've got a public key, private key pair. You can sign off on transactions. This is not the case in Bitcoin, right? In Bitcoin, you have a full node. Your full node might have a wallet associated with it, with public keys and private keys, but the node itself does not. Possibly in the future, there's BIP 150, I believe, which the idea is to have encrypted communications between nodes, which would have some kind of authentication. There's BIP 150 and BIP 151. I might have them backwards. 151, I believe, is just encryption, so for privacy, sort of confidentiality, and then BIP 150 is for authenticity. So if you connect to a node, you're like, oh, this is the same node at the same IP address that I connected to before. They're not implemented yet that I'm aware of. So right now in Bitcoin, when you connect to people, you sort of just use their IP address. You don't really know who they are. There's no authentication there. But in these, in Ripple and Stellar, you do know, okay, I'm connecting to this node. It's got a key. It's got an identity. So to sync, instead of verifying all the work, you verify the signatures on blocks. And the question is, whose signatures, right? So if you assume, okay, well, if we have a majority that's honest and is not trying to, create transactions that are invalid or something like that, then it might work. But majority is hard to define when you're subject to Sybil attacks, right? The obvious attack is I just make thousands of nodes, or maybe these nodes don't even really exist. I just make thousands of key pairs, have them pretend to be nodes in my own sort of subnetwork, and they all endorse blocks that are different than the rest of the network is endorsing. So majority is the tricky part. How do you know who's the majority if you don't know who these people are? You need some kind of way to identify humans or computers even. And this is a problem akin to certificate authorities. And I just wanted to sort of, a lot of the problems that you see in like blockchain, Bitcoin, these kind of things are not exactly new problems and have sort of already been quote unquote solved. So does everyone know how CAs work? Or do people have some idea? Or who's like, what's a CA? Okay, so it's kind of interesting. I can give a little demo. Uh-oh.
Did you say CA stands for Certificate Authority?
Yes. Uh-oh, this doesn't work. Hold on. Okay, so if you have a computer, I don't know where it is in Windows, but I think in Mac and Linux it's in the same place. You go to Act, and then, shoot, I forget where it is. Where, yeah, where's the certificates? There it is. Okay. So in your computer, and whether you have Linux or a Mac, you've got a folder somewhere, etc/CA certificates, something like that in Mac as well. And, oh, well, no, that's not it. Where are they? Shoot. Wait, what is in update.d and then there's nothing there? Hold on. I need to find this because it's kind of cool. Where are SSL, is that? There we go. Okay, so, sorry, etc/SSL, and then you've got certs. And this folder has a bunch of certs. I trust all of these entities. Well, my computer does. And by extension, my browsers and my computer. Which is crazy because I have no idea who these people are. Turk Trust? I don't really trust Turkey. Swisscom. Swiss people seem nice, I guess. I don't know. But there's, okay, they're in Netherlands somewhere. There's a bunch of, you know, like just things you've never heard of. Hellenic academic and research institutions. Hong Kong Post. Hong Kong Post Office seems trustworthy. Yeah.
One you pointed out, they actually in the past signed SSL certificates with Google.com when they weren't supposed to. They made a wildcard certificate.
So there's a lot of, and then like CNNIC is one which is like, is that still in here? Maybe they got rid of it. And then some of them just have these numbers and you don't even know, you have to go in. Yeah, China Internet Network Information Center EV certificates root. I'm sorry. I don't, okay. I actually really don't trust them to endorse sudo rm. There we go. Okay, it's gone. Solved it. Solved the distributed internet trust problem. But
now part of the internet doesn't work for you.
yeah, well, I might get invalid certificate errors for some Chinese sites now. I don't go to many Chinese sites. Anyway, so that's the basic idea of certificate authorities. And this started in like mid-90s when they wanted to make public key infrastructure for secure websites. One of the problems is how do you know, like, so you've got, oh, we didn't talk about Diffie-Hellman, or maybe I mentioned it, but you've got, you know, public keys, private keys, you've got ways to do signatures. Diffie-Hellman is a way to do key exchange, so you can have, you know, if I know your public key and I give you my public key, we can form a third, basically key that we can then use for encryption and secure messaging. This all works, but how do you know, given a key, who is on the other end? So that's the idea of certificate authorities. You have this sort of root of trust. And these certificate authorities sign certificates in websites and let you know, oh, this is the person who you think it is. So for example, Google, secure connection. Really? How do I know? Verified by Google Trust. Well, Google has verified that Google is trustworthy, which is somewhat circular. But no, that's sort of how it works. Yeah, so Google Trust Services is a certificate authority. They ultimately, yeah, and they signed off their own certificate for their own website. That's maybe not the best example. There's other, okay, the New York Times. They are certified by Komodo CA, who also has had, like Komodo's gotten in a lot of trouble for signing the wrong things. So yeah, New York Times does not have an EV cert. I think Washington Post does. So there's also EV certs where like, you've got now the Washington Post WP Company LLC. That's like an extended validation cert, which then the CA is saying, we didn't just check that they had an IP address and a domain name. We actually checked that they had some kind of legal corporate entity. And they sent it on their letterhead, and we, I don't know, emailed someone in Delaware to make sure they actually had a company. And this is verified by Entrust. Okay. So Entrust, Komodo, those are all going to be in here. Yeah, there's Komodo. So you've got these companies called CAs that have some kind of agreement with each other. There's sort of these standards where you make some kind of standards where, okay, don't sign the wrong thing. If you do, we're going to delete you. And then they all sort of endorse entities' identity, usually for companies. There's also stuff now, Let's Encrypt, which does it for free and without really endorsing anything. So this whole thing was kind of, it sort of felt like it was like the big scam of like the late 90s because they made billions of dollars. But then again, we got, you know, Ubuntu out of it, right? So yeah, Ubuntu was funded by Mark Shuttleworth, who started this one, I believe, and made a couple $100 million, went on the spaceship, went into orbit, had some fun. You know, eccentric billionaires are what fund a lot of technology development. And this is how we get them. So CAs are, a lot of the people who work on Bitcoin and these systems feel that like the current, it's called X509, it's like the name of this whole system with these certificate authorities. And I also sort of feel that this is a suboptimal solution in that there's a lot of problems with certificates being signed inappropriately. It works in a way, but it's like not great. So this is a problem. So the problem that these systems like Ripple and Stellar have to deal with are in some ways similar to the problem that is solved by CAs. So what they do is they say, we have a unique node list. We're not actually endorsing an identity from, you know, here's a public key, here's a human company, you know, human name or a company name or something like that. We're just saying that they're unique. So it's more limited than a certificate authority. It's just saying, we're certifying that these two keys belong to different people or different companies, which seems easier than the job of the CA, right? The CA has to verify that like the Washington Post is actually the Washington, you know, the key, whoever's presenting a public key is actually the Washington Post. So the actual certificate is just basically, here's a pub key, here's a name, and then the CA signs. And you can look at those and stuff. Okay, so for synchronization, you wait for a majority of nodes in your unique node list to sign. And if they've signed, accept. So there's some recent papers from Ripple. And in order to really get consensus, you need basically a 90% overlap in your unique node list. So if I have a unique node list of Allison, Bob, and Carol, and you have a unique node list of Carol and Dave and Edna, I don't know. We might diverge. We might not agree on the same sort of chain of transactions because we've got different people that we're looking at their signatures. They may all be unique, but if we have different unique people we're looking to, it might not converge. So they have a newer paper that reduces that to 60%-ish, where the overlap of what unique nodes everyone needs to look at is not as large, but still quite large. And then the real question is, okay, well, who provides the unique node list? Because how, you know, that's not really a job I can do. Maybe it is in a way. If I know you and like we do some kind of web of trust thing where I'm like, oh, what's your Ripple nodes pub key? Okay, cool, I know you. And what's your Ripple nodes pub key? We meet in person, we sign each other's pub keys, we do the whole PGP kind of thing, which, you know, I do, and the Bitcoin people actually do this. So if I go to, so I've got like a bunch of keys and everyone signed them, and there's like Andrew Chow and Suhas and Kale and, you know, all these Bitcoin people, and I've signed their keys and they've signed my keys because we meet in person and do that kind of thing. So we've established not just a unique node list, but we've done a CA-free validation of each other's keys. We just meet in person, read each other's keys off. So you can do that. In practice, it's really nerdy, and no one does that. And and it would be cool if we could get it to be easier and maybe cooler somehow. But it's been an uphill battle. So who provides the UNL? It's probably kind of obvious. Well, the Ripple company provides the UNL, right? So when you download Ripple, it has a list of unique nodes. Those are essentially de facto the nodes that run Ripple. And at the current time, they're basically, those nodes are run by the Ripple Corporation. Or Ripple Labs. Stellar, similarly, like it comes with a default UNL. Sort of acts like the CAs, right? It's sort of how when you start your computer, you've got this. This comes with your OS. And you don't really have a choice. In practice, you can, I just deleted the CNNIC one, but nobody looks at this stuff. Everyone just goes with the defaults. So that's the problem centralization-wise. Yes?
You said Ripple or Stellar actually run the nodes? Because I understand that they might sign off on the UNL, but you're saying that...
In Ripple's, at least like a year or two ago, they may have changed that. I think they're trying to, but in Ripple's case, yeah, they ran their own Ripple nodes.
So it's not the bank partners or anything?
They may have some, but they may now, but I know that 2 years ago it was just Ripple, or majority Ripple. They basically, because they also put in things like they can sort of freeze funds because Ripple got in trouble with FinCEN, and part of the thing is they modified their code to be able to like freeze people's funds if they did something bad. That's definitely not something that the Bitcoin developers or even like the Ethereum Foundation. It's not as direct anyway. The Ethereum Foundation sort of did freeze funds and move them against the rules of the system in the case of the DAO, but that was in a lot of ways with support of a lot of the people running Ethereum. With Ripple, they can do it sort of without much brouhaha. They just sort of freeze these funds. So it's fast. There's no work involved. There's no worry about propagating blocks and miners getting advantages. But there's also known identities, and so it's sort of more susceptible to subpoenas and things like that. All the coins, in these cases, all the coins existed at the Genesis block. So in the case of Ripple, I think it was 100 billion or something. And they just started with all the coins and sort of distributed them as they saw fit. Same with Stellar. Stellar had this thing where they had this party and they would give them away if you signed up on Facebook. Really interesting article about people in Manila getting thousands of used SIM cards from the US, registering for new Facebook accounts, selling those Facebook accounts to people in China, the people in China then registering with Stellar as unique people to get more Stellars. When you incentivize things, weird things happen. Be it either giant warehouses full of SHA-256 chips or giant warehouses full of 20-year-old girls in Manila putting SIM cards in cell phones all day. Yeah, I should link to that article. It's really interesting. So anyway, so this is Stellar 1. And Stellar also had this thing where they were going to give 20% of the Stellar to people who held Bitcoin, sort of an airdrop. I didn't get any from that. It wasn't, I was sort of hoping, I'm like, hey, cool, airdrop, I have Bitcoin, I'll get some Stellar. I didn't, because you basically had to KYC with them. They said, okay, send in your, I don't know if it was a social security number, but send in your documents and prove that, you have these Bitcoins, and we will credit some Stellar to the same keys. And I'm not going to do that. Yeah, some people did. Some people got some Stellar that way. But, yeah. So anyway, yeah.
Wait, is Stellar's freezing coins? I mean,
No, I don't know if Stellar has that capability. Ripple does. Ripple put that in. Stellar is a different, it's similar software. They certainly argue about how different they are. Stellar had a bug in 2015, I believe, where the sort of consensus broke, and then they said, "Oh, it's Ripple's code's fault. This is a fault with all this code base." And then Ripple said, no, it's because you changed it and you don't know what you're doing. So they.
I was talking about, I guess, the minimum.
The,
You said there's minimum.
yeah, there's a minimum account balance.
And if there's a set number of coins, and eventually accounts just get.
Yeah, I mean, it's a lot though. There's hundreds of also, there's enough for I mean, there's a lot of coins. But yeah, I guess the idea is not that you have UTXOs like in Bitcoin and you sort of make new addresses each time. The idea is you have an address, you keep that forever. So why would you have multiple different addresses, that kind of thing. Anyway, so it's a pretty different system. In some ways, you could argue it's one of the first ICOs, Ripple, because it's pretty early. They just came up with all their coins and sort of gave them out, and then started selling them. And they continue to do that to this day. Stellar is a nonprofit, which is also sort of weird because if you make like $1 billion off of something, is it really a nonprofit? I don't know. The organization didn't directly make the money and then pay it to the employees or anything, but the people who have all the Stellar tokens made a lot of money. Interesting sort of ways to do it. So I think both Ripple and Stellar argue that it's decentralized, distributed. But I think a lot of people say, well, maybe to some extent, but on the spectrum of like completely decentralized versus, one server handles it all, it's a lot further on the centralized side. And Bitcoin is also kind of centralized too, like we were talking about on Monday, but I would argue these are more so. So anyway, any questions about Ripple, Stellar? It's pretty fun. Okay, the big one, proof of stake. So we've mentioned a little bit, it's a popular alternative where people really don't like the proof of work stuff. So instead of proving work, have the people who hold coins sign the blocks. So you don't really, that sort of bootstraps in a way your unique node list or your list of who's who. Well, you don't really care who they are, but if they have coins, if you already have a set of who owns what coins, you can use that to say, okay, well, the people who own coins now sign. And they presumably have incentives not to destroy the network they have coins in. So if you have a given genesis block with some kind of initial distribution, you can make it deterministic. You can say, I'm just going to go with whatever has the most stake, whoever has the most coins signing off on the next block. And given 2 or 3 different histories, you can see, okay, from the start, which has the most total stake signing off on these things. So that seems pretty cool. Here's some issues. Stake grinding. So for example, let's say you have a system where the signer of the next block is determined by the public key nearest to the previous block hash. So for example, okay, I'm looking at the current block hash. Who gets to sign next? Well, whoever's key is closest. Use XOR, just treat the hash as a number and treat the pub key as a number and see which is closest. You can do that, but the problem is, if the next hash is determined by the current signer, that current signer can sort of make a new signature each time and try to make sure that the block after is also going to be one where they are, again, the next signer. And they can make a couple hundred different accounts with their keys, and then keep grinding stake. And this basically means that it turns into proof of work. Because if you can influence who's going to be the next block signer yourself by keep trying different ways to sign, okay, that's basically proof of work, but instead of hashing, you're signing. And this has happened in many altcoins. One that I think was kind of interesting was NXT, which is the people who later went on to make IOTA. They said, okay, well, we have a deterministic signature scheme, and so this can't happen, right? Given a message and a public key, given a message and a private key, there's only one signature that can be produced. And this is true. So Bitcoin uses this. It's called RFC 6979. So basically, the random nonce can be deterministically created from your private key and message. The problem is, I don't know if they realized, probably not, but you can't enforce this. You don't, it's a policy that says, okay, I'm going to make a deterministic signature. But given a signature, you can't tell if someone did this or not. right? So it's up to you to obey this rule, but you can't verify that anyone did it. So that one also quickly devolved into proof of work, and in a tricky way, because a lot of people read the documentation and said, okay, well, there is no way to keep signing. If their function that they wrote, there's only one way to sign. When you sign a message with a public key, you get a single signature. But people who knew how it worked under the hood said, oh, I can change this code. It will still be accepted as a valid signature, even though I'm using a different signing scheme. So this is one issue, state grinding. There's ways to get around it. So let's say you make it deterministic. You have some way to enforce that a signer can only create one message. There are certain signature schemes where you can verifiably make sure that a single key can only make a single signature on a message. Other ways to do it is to say have this big lead time where the people who are signing the next block are determined by entropy created days or weeks ago. So it's hard to know what's going to happen in a week because it's a long period of time's worth of entropy going into it. Okay, there's another issue with proof of stake called nothing at stake. So rehash. So in proof of work, this happens, right? This happens just by accident, where okay, there's a block, and then two people are mining on top of it. Oh, they both got this, and then sometimes even this. That's almost never happens in Bitcoin, but sometimes where you just randomly get two sort of split chains coming out at the same time. But then this happens, right? Someone builds on this one. Okay, you get rid of those two. And that's just because, this is a random process. You can mine on whichever you want. One of them is going to happen first. You can mine on both. You can split your hash power. If you have 1 billion hashes per second, you can say, well, I'll do 500 million here and 500 million here. You can equivocate. It's sort of equivocation that way, but one of them will finish first with, very high probability. So eventually this happens, and then everyone just starts building off this 00A3. Proof of stake. So this happens. Also, notice that the hashes they don't start zeros. So this happens, but then this happens, and then this happens, and then it just keeps going, because why not sign both? Right? I don't know which one's going to win. Right? As a proof of stake sort of miner or staker, I don't really know which one's going to win. Which is the same case in proof of work. In proof of work, I just flip a coin and pick. Right? I don't know what's going to win. I think in Bitcoin the default is go with the one I saw first, because maybe whatever. It doesn't matter who wins, right? Basically I win whichever I pick. If I'm the next one making a block, I win. But what I don't want is I don't want to be what I don't want to be in proof of work is I don't want to be 0088. Right? I don't want to be the last one to make a block and then something else comes out here. So if I see, I'd rather be 00F2. But you don't know here, right? So you just pick one. Okay, well, we lost. In proof of stake, you don't have to worry about that. I'll just build both, right? It takes me no work to sign, so I just sign off on both of them and make parallel chain, and then everyone just keeps doing that. Because if I pick one, I might be wrong. If I pick both, I can't be wrong. So this is a problem called nothing at stake. Like, you have no risk here. You're not actually doing any work. Might as well just keep going. So yeah, faced with two blocks, why not sign both? So the mitigations. One of the ideas early in Ethereum was, okay, this thing called slasher, where if you can prove that a signature from a different chain, so the idea is on chain 00A3, on this chain, you say, hey, look, this guy equivocated. He signed off on 2 blocks, one of which exists in my history that I can point to. One of which doesn't exist in my history, but I can provide that signature. I can say, look, here's 2 signatures at the same block height, but from the same person, but they're signing different things. Let's not invalidate this block, but let's take all the rewards from the person who signed. Okay, so yeah, this is called Slasher. I believe in Ethereum, like 2014, they were sort of saying, hey, we're going to do proof of stake. And then they sort of tried all these things and sort of, oh, it's non-trivial. Let's start with proof of work, and then we'll move to proof of stake later. And that's currently their plan. So this was one of their early algorithms, their early ideas. There's also issues with the mitigation, because maybe it's hard to get this proof into the blockchain, because the miners or the stakers are the ones who determine what gets in and what doesn't. And so they certainly could say, look, if you provide, so if the, wait, this is, if the person who created this block then sees in this block that there is a slasher proof where, hey, I just now prove that you equivocated and destroy your account. Well, the person who signed this doesn't build on this and instead forks off and builds their own, right? Why would I continue to mine on a chain where I just lost all my money? So there's all sorts of weird, and there's mitigations for that. So it's a little bit whack-a-mole where there's all these weird problems and you have to sort of try to fix them, and then fixing them introduces new weird things. So there's a lot of people working on it. Yeah, long-range attacks is another big one. Let's say you go back to the Genesis block and you rewrite history. In Bitcoin, you can also do this. It's just really hard, right? You could say, I'm going to get a bunch of miners, rewrite all 9 years of Bitcoin's blocks, and we know exactly how long that will take. SIPA has a nice graph of it, I think. And sometimes it's not very long. Sometimes it's actually pretty easy to do that. Yeah, that's the other side. Hash rate. Yes. Bitcoin network, proof of work equivalent days. That's this year. This is since the beginning. Where what this means is, okay, given the current hash rate in Bitcoin, how long would it take to rewrite the entire history of Bitcoin? Because the hash rate goes up, right? And sometimes it goes up in, so this is the all-time hash rate. It basically always looks like this because it's exponential. So if you looked at it 3 years ago, it would look pretty much the same. And then this is a log chart. So this actually does show some interesting detail where, okay, this is when the GPUs came out, this is when nothing much happened in 2012, this is when ASICs came out, and then sort of it just keeps going up. And this is log scale where each number is 100 or 1,000 times, so it's big. But so when you have these really sharp upticks, like in mid-2010, the current power of the network is so high, that probably corresponds to this, the lowest point there, because that's the steepest slope, where, I don't know what this is, a week, you could rewrite the entire history of Bitcoin in a week. And destroy everyone's currency, and have all the coins yourself, if you had enough power and under your control, which you could probably do. And today it sits at around 200, a little less than 200, so a little over 6 months, where if you devoted all the current hash power, you could rewrite all the previous history. Still, 6 months, it's a lot. And it's interesting how this changes. This is, I guess, when the ASICs first came out and the slope went up a lot. So that is an issue in proof of work that can happen. It's not clear what would happen. Would the Bitcoin software, the software, at least in theory, the idea is if something like that happens where there's a reorg that spans 9 years, well, extend this out to 500,000 and say, okay, all the stuff you've been dealing with the last 9 years, it's out. We've got this new history now with one person owning all the money, presumably. The software will do that, probably, or it'll just crash or something. Because it's sort of seen as well, if there's a reorg that spans weeks or months, the whole system's broken, kind of. But probably, so this is an issue for Bitcoin, but it's a big issue in proof of stake because it seems possibly more feasible, right? In Bitcoin, there have been times it's whoa, a week, yeah, that's feasible. Whereas right now it's like, okay, it would take all the hash power in existence, maybe 7 or 8 months. So that means that Bitcoin would just halt for 7 months, and then you'd see this reorg happen. It seems, and it also it assumes 51% of the miners are doing this. However, with proof of stake, it might not be that expensive, especially if you can get old keys. So if you've got the keys from the Genesis block in your in this proof of stake currency, you can rewrite a history from those with different transactions. So yeah, so a lot of times the solution is, okay, well, delete old keys and assume 50% honest. That's tricky because old keys can be sold. And people have been, I know that people have asked, like, hey, can I buy your old Ethereum keys? Why do you want these? Well, if proof of stake happens, they might be worth something. Currently, if you have keys that are for addresses or accounts that don't have any money anymore, it's not very useful, but possibly can be sold. Yeah.
Most proof of work schemes that I'm aware of use the coordinates to deal with this one.
Proof of stake?
Yeah.
Yeah, so you checkpoint it. So basically, to prevent long-range attacks, the developers usually in GitHub will just say, okay, well, the block height, the block hash here is this. And so you can't reorg before that. But then what's the mechanism for that? If it's the developers just sort of sticking in a checkpoint, that's not really decentralized.
The example of Peercoin has actually a checkpointing server that every few hours endorses a block height.
Okay, well that's even more sort of not very decentralized if you've now got a pub key hard-coded into the code, which then calls out to somewhere and says, okay, what's the correct block to be on? And then that key signs something and says, oh, go here. Okay. That's pretty centralized. So this is one that I think it's hard, right? Because before these things happen, it's easy to dismiss as like, this is crazy. That's never going to happen. Who's going to go back and buy up all these old keys that people were supposed to have deleted? People probably did delete them. You can't assume that they haven't. And even if they did, and you made this big reorg, well, everyone would know in practice that that's not the right chain. Similar to how if there's a 9-year block reorg in Bitcoin, everyone would know, okay, come on. We all knew what the blocks were yesterday. You can't just tell me there's this entirely new history today. And in practice, that's probably true, right? If there was a 9-year block reorg in Bitcoin, probably people wouldn't would just ignore it. Similarly, in these systems, probably they would ignore it. But it's harder to reason about in these systems, I think. But anyway, so proof of stake, there is a bunch of coins that use it. In a lot of cases, they sort of have centralization that's sort of hidden in certain ways. I like the term Greg Maxwell came up called trust laundering. It's not money laundering, it's trust laundering. Like you sort of move where you're trusting and try to hide it. Yeah, so a very common, but this also deals with, okay, who gets the initial coins because they have an enormous power over the system. So very common for altcoins, less so now, I think, was start with proof of work, then transition to proof of stake. Do they still, not as much.
Now you don't need to do that because you have Ethereum.
Right, so you just do ERC20, yeah. But it used to be like 2014, 2015, a lot of the coins would be, okay, proof of work for the first month, 2 months, whatever it was, with some weird algorithm and Komodo gravity well and all sorts of weird stuff. And then it would switch at a certain point to proof of stake. So that proof of work period builds out the list of who owns what in a sort of provable way. And then from there, you can use proof of stake because you've got a hopefully fairly well distributed set of who owns what. Yeah, no, some things still do this, and some things have hybrid where you still have to do work each block, but depending on how much stake you have, depending on how many coins you have to do less work. I think Decred is something like that. That actually can make sense because you've still got work, and you could mix them in ways that sort of negate some of the downsides of both delegated proof of stake. Well, signing requires you to actually do something and be online. So in a lot of proof of stake currencies, very few people actually stake because they don't care. And they leave money on the table, sure, but like they don't want to run their own node, they don't want to deal with this stuff. They just buy it, keep it on exchange, or maybe keep it on their own computer. So instead, you can endorse a leader by signing with your coins and saying, hey, I'm not going to actually sign off on blocks, but I'll sign off on a different key who now can sign on my behalf. And so this can be called like super nodes, master nodes, and then is it peer-to-peer or is it client-server is what sort of it becomes. So the current one that's pretty popular is called EOS, where I think they're doing this kind of thing. And they're like, well, there's 20 computers that run the network, and you can endorse one of them and they'll give you some kind of profit back or something. And you need like $1 million to run one of these computers because it's going to be super powerful and you can do free transactions that way. So this gets pretty far into client-server territory where you're not a peer, you're just the client and you ask them what's going on, which in many cases works, right? But then again, it's not quite as interesting because that's sort of the system we already have with banks. So, but in a lot of cases, yeah, that's what people want. I sort of joke that I should just make one called Central Coin, where there's just a nice server and it just keeps track of who owns what, and then like have an ICO and people would use it. And it's like, hey. So I think people would be into it. Anyway, so that's distributed proof of stake. Okay, so proof of stake in general, it's hard to resolve conflicts using only the system itself. Proof of work has this really nice property where it's taking something from the external world, be it, you know, CPU time, be it chips, and using that to sort of get a sort of dead reckoning on the system itself. That's nice. Proof of stake, the really difficult part is it's a closed system. You're trying to resolve conflicts within the system using no external data. That's really hard. Another problem people complain about is that the rich get richer. I, agree it's a problem, it kind of sucks, but, proof of work is the same. I don't feel like any of these systems will change the inherent sort of Pareto distribution of wealth in the universe. That just seems to be how things work. It'd be cool if everyone had the same amount of money, I guess, maybe, but I don't think it's going to happen. Yeah, and then it relies on different assumptions. So the assumption in Bitcoin is like 51% of miners can destroy the system. So in some cases, people say, well, you assume 51% honest in Bitcoin. Kind of. It's more like 51% rational. In Bitcoin, you could have miners with 51% attack the system, but they make more money by doing the right thing. So there are certain cases in proof of stake where honesty is not as profitable. And if honesty is not profitable, well, maybe there's a lot more incentive to be not honest in the terms of the system. Whereas in Bitcoin, it's like you've got this nice system where it seems like the honesty is not just enforced by people trying to be nice, it's enforced by people being greedy, which seems more common than being nice in the world. So there's tons of research in proof of stake. Some of it's pretty interesting, pretty clever. I'm not super hopeful, but the thing is it works until it doesn't. And so it's really hard to show security like under what different attacks. So what I would worry about is you've got this proof of stake system, seems to be working, and then something weird happens and it's sort of revealed as, oh, actually this was a lot more centralized than it seemed to be. Which is also a worry in proof of work. Okay, any questions, proof of stake? Yes?
Quick one on the economics. Is the stake the nodes have? Right? So
Yeah.
in essence, if it was on EOS, it's how many EOS coins you have.
Yes, yes.
So then there's probably some economics where people who are not miners will lend their stake to get a return.
Basically, yeah. And it's a lot of coins, the majority of the coins are held on different exchanges. And so that means the exchanges would possibly be able to then stake and get some kind of
So they would be
revenue.
taking their customer funds that are in wallets.
Yeah.
They'd have to be probably hot wallets. And then the exchanges would have a leg up to be the miners.
Yes.
Or earn a fee lending.
Yeah, and so that's also an issue, that there's all different sort of ways to mitigate. And you can say, oh, I'm in an exchange, but I get to sign and sort of delegate my stake to someone else, and then I get some kind of revenue sharing from that. But yeah, it's also tricky. How do you incentivize it in terms of how much new coins get issued to the people staking. If it's 0, then there's no real incentive to do it. You could have a lot of different chain forks. If it's very high, then it's like very, I don't know, Gini curve goes way crazy because the rich really get richer because the more coins you have like an enormous amount of revenue. So you sort of need a balance there that's also a bit difficult economically. That's also a problem in proof of work. I feel like one of the big issues with Bitcoin is half the coins came out in the first 4 years where like hardly anyone was aware of it. And that makes people not want to adopt the system because it's like, well, wait, you guys just got all this coin for basically free. You're just like running your computer in like 2011. I'm not going to be part of that system. So I sort of feel like it would have been nicer if it was more of an S curve and less of a log curve, because then maybe it would like ramp up in like 2015 and then lots of coins were coming out. But anyway, that's so like Ripple or Stellar are sort of an extreme case of that where all the coins were initially made by one entity. And so to me, I'm like, I don't want these. Like that's your money. Like you just made it up yourself. There's sort of a like, I don't know, it just feels like kids being like, I have $1 bazillion and I write $1 bazillion. It's like, okay, well you just wrote that. Like I'm not going to honor that. Anyway, okay, so proof of stake, kind of interesting. Proof of space, there's a bunch of ideas here. Some of them, Space Mint was some people here. I know Bram Cohen, who is the author of BitTorrent, right? He made BitTorrent, whatever, 10, almost 15 years ago now. He's now working on some of these kind of things. He's working on a proof of space coin called Chia. And the idea is, it's still similar to proof of work, but you're using some kind of memory or storage space rather than your CPU. And the idea is the benefit is, well, maybe it doesn't use as much electricity. And also from talking to Bram with he's saying there's much more sort of dead storage space than dead CPU. So every computer has a CPU, but like the CPU here is not that powerful. It can't really compete with ASICs. But lots of people have empty hard drive space. And you might have a terabyte of empty hard drive space. And 1 terabyte's as good as another. And it's also empty is what you need because you need to fill in space for these systems. And so if you're like, well, I'm AWS, I've got, tons of hard drives. Right, but people are using them. So you're not able to then just like fill it in for these kind of systems. Well, to some extent. They do have a lot of slack and they can probably do this. But several ideas, some are pretty cool. So one example this is sort of an example idea. It's not fully fleshed out, but to give you an idea. So you buy a 10 terabyte drive, okay? You pre-compute 100 billion key pairs. And this takes a long time, and this is work, right? You're doing 100 billion computations of coming up with a random private key, multiplying by G, getting the pub key, and you store it in a key value store, like a database, LevelDB or something, on your hard drive. And the key is the pub key, and the value is the private key. So you remember your key pairs, but you've sorted it in a way so that you can quickly go through the pub keys, right? So you have like login, search time, some kind of binary tree, whatever it is, in your database. And so then the idea is to create the next block, you want the key closest to the current block hash can sign. So a valid proof of work, you have some threshold maybe. A valid proof of work is whoever's got a key that's very close to this, they're able to sign. And those keys do not exist on the network prior to the signing procedure. They exist just hidden on people's hard drives. And so the idea is you could just try to keep computing keys till you find one and then sign with it. And that would just make it completely proof of work. So it is proof of work, but the idea is you can pre-compute. You can do all the work beforehand, and then you can use that pre-computed proof of work later on, and possibly multiple times. In practice, it's not going to be multiple times because you've got 100 billion, and you're never going to like use the same key twice. And the idea is everyone does this, right? So you have trillions, quadrillions, however many keys out there that everyone's generated, and every block that comes out, someone will say, I was lucky and I made a key that can now sign the next block. So it's work, but it's amortized over weeks, months, years. And it's basically how fast, how big is your storage? If you have a lot of storage, you can pre-compute a lot of this stuff and then use it. So it's kind of a cool system. We'll see. There's sort of other asterisks. It actually gets a little more complex because you need some timing mechanisms as well. But I think it's a cool idea. Hard drives then maybe get more expensive instead of graphics cards getting more expensive. I don't know. But the idea is like, yeah, you use the work, but later on. So, any questions about that one? Kind of cool. There's a Spacemint, it's a cool paper about how to do this cryptographically, and then Chia is another one doing this kind of idea. I sort of like it because it doesn't really change the assumptions of proof of work, right? It is still a form of proof of work, but instead of burning electricity, you're using hard drives, and kind of cool.
Wouldn't you still have the same issues? Like you just have ASICs just filling, racks and racks and racks of hard drives with keys.
We're sort of already different. You sort of already have that, right? Like there's server farms where they're just storage farms and they just have tons of hard drives. So that's already a thing.
But I'm just saying it isn't any different. I mean, you'd still be, it would be in your interest to spend as much electricity.
I guess the idea is the economies of scale are not quite as bad in that hard drives are already basically optimal at doing this. And if you can make a system that's better at doing this, you've just made a better hard drive. Which, hey, great, you made a better hard drive. Everyone can use it. So I guess the idea is it's not as specific because it's just, hey, store a bunch of data and then see quickly through it.
Still seems CPU bound, right? Compute bound.
No, once you generate this, generating this is compute bound, right? You need to populate your 10 terabyte drive. But that might only take a few hours, right? To make 100 billion key pairs, I'm guessing less than a day, right? Yeah, and you can do that in parallel. So you make it, and then once you've made it, you leave it there, and then you're going to be able to mine with that forever.
But it seems like the winner would be whoever can fill the most number of keys per second going forward.
But you need something to fill. I think the hard drive cost is much higher than the cost to fill it. Right, because a 10 terabyte hard drive is going to be like $200, but you can fill with a cheap CPU, you can fill a 10 terabyte hard drive every few hours. So I think that the CPU is a factor, but I think it's going to be smaller than.
At least from what I understand about Spacemint, the idea is to make it not I/O bound as well. So if I have a better or faster hard drive than you, that's not the quantity that's actually important. It's just how much space.
Just because this is just a seek. Right, and even a crummy hard drive, you just read through your binary tree and you're like, oh, found it.
I think the point is you're only supposed to do one of those per block that's created. So
yes. You just say, so you look at, okay, here's the current block hash. What do I have that's close? Seek to that on my drive. Nope, I'm not going to win this one. Okay, let someone else do it. Or you seek and you find it. And you're like, hey, cool, I can sign. So, yeah.
Is this also known as proof of space time?
Yeah. So that's in Chia. They sort of add this time component, which I'm not 100% clear on how it works. It's changed a little bit. But you want, so the idea of a time beacon is you want some function that cannot be parallelized so that if you have 100 computers doing it, it's not going to be any faster than one computer doing it. So basically, whoever's got the fastest single CPU will always win this. And that can be sort of a time beacon for these space things.
Once you start to have a lot of storage, if you have to search to find a matching pair, you kind of go back to, if you're almost getting hurt compared to that, I don't know. You know what I mean? Like, you have so much storage that it's almost like you're just doing the same thing again.
I think that's a solve. I mean, if you have like tons of hard drives and you want tons of key values and you just want to find one or find the closest match, like you can do that in log n time, even over a whole data center. Like Google, like you just search and it's like, hey, it comes up in like a fraction of a second. So that's doable. You need good software and you need like a good infrastructure to do it. But I think it's doable. It scales pretty well, I think. But yeah, it has the same issues where like you just end up with people buying a whole bunch of hard drives. And like, what are the economies of scale there? There's arguments that it might be better than the economies of scale with like ASICs that we heard about on Monday. Maybe not. I don't know. We'll see if this takes off. It's like fairly new. It's an idea that's been talked about for a few years, but.
The coin called Fast Coin. Those do proof of space, and they've been around for years, and it's not.
Okay. Well, so there's different ideas. I don't know. It seems like one of the more interesting sort of. There's cool math and cool crypto involved. Okay, so work but amortized. So a perennial MIT favorite, IOTA. They use a directed acyclic graph, and now a chain is also a DAG, because it's directed. There's no cycles, and it's a graph, but it's a pretty simple one. But the idea is have multiple parents, right? So if you have a block, instead of just pointing to one, you could say, well, now this can happen in Bitcoin, right? Where you've got two blocks both pointing the same thing. But this cannot happen in Bitcoin, where you say, oh, I'm coming off and I'm referring to both of these. But in a directed acyclic graph, you can do that. So Ethereum actually does this. I think Joe Bonneau was mentioning that. And so what happens is you sort of endorse one as the correct one and one as the uncle. So you're saying, no, this is the real one. But I also saw this one, and give this one a little bit of money, right? Maybe not the whole reward they were hoping for, but they get something. And so then something like IOTA says, okay, we have lots. And every node points to two previous, and so you get this whole map. They can even point to different heights. So I can point to here and here. I don't really know why you do this. I guess, so there's some ways it could reduce latency, right? So one of the trade-offs in Bitcoin is 10-minute block time seems fairly arbitrary. It's kind of slow. Latency, people don't like latency because they have to wait, fine. The more important metric, I think, is that it leads to minor centralization and minor pools. Because if there's only 144 blocks a day, which, like in Bitcoin, if you have a millionth of the hash power of the network, you're just never going to find anything, right? If you're just mining on your own, over the course of a year, you're probably not going to find a single block, and you'll have wasted all of that effort. So instead, you join a pool and try to, pool with other people to distribute those rewards. However, if there's like an Ethereum block every 15 seconds, and there's millions of blocks that come out, if you have a millionth of the hash power, you might find a block. The blocks have smaller rewards, but it's like, chopping it up more finely is a nice way to do it. So like P2 pool, which you work on, is a sort of way to try to make that. And it's important to get it more decentralized, but it's hard. Yeah.
Pool also does that.
Yeah. Yeah, P2 pool sort of does this as a layer on top. So it could help latency, and then it could help reduce the amount of orphans in the blocks, in the blockchain, which then helps minor centralization. So there are interesting ideas for it, but it doesn't help scalability at all, right? It actually hurts scalability, because now I have to keep track of all these things instead of just one chain. And I'm going to have to keep track of all the data anyway if I've got the UTXO set. I can't just ignore parts of it. So it doesn't help scalability at all. And in the case of IOTA, their custom ternary hash functions also don't help much either. So that was sort of what we wrote about last year. They made all their own weird stuff. I don't know. So there are interesting ideas between directed acyclic graphs, but it feels like when they say, hey, this is more scalable, I get very suspicious, because like it doesn't seem to help scalability. It does possibly help some other things. Yes.
It's effectively Bitcoin regression test mode. They've made it so every block is min difficulty, and so the transactions are instant because it doesn't.
What, in IOTA or in
any of these DAG coins?
Yeah.
So it doesn't cost much to make a new block and make a transaction, and if everyone's competing to do that, then you're just going to have a ton of orphans, and you have to wait all the time.
Yeah. So also in the case in IOTA, the idea is, well, they don't call it this, but it's the equivalent of saying every block must have one and only one transaction. The transactions themselves have proof of work on them, and they point to each other, which basically is the same as, blocks have one transaction, and you do the work yourself instead of paying a miner to do it. I think that's not a great deal. And they say that means there's no fees. I think it's kind of, there's still fees because you're just doing the work yourself. I think that's equivalent to saying there is a refrigerator at Home Depot that doesn't use electricity, so hey, it's electricity free, but there's a crank on the back, and you have to crank it to make the refrigerator cold. Yeah, you could make a refrigerator that way. I don't think people would want it. You're still doing the work, you just have to crank it instead of plugging it in. So the idea of like you don't have to pay miners a fee to get into a block because you just mine the block yourself, or in this case, you mine the transaction yourself. Doesn't seem that useful. Anyway, so IOTA's fun. We've talked about them a while ago. Okay, last one that's fun. Proof of idle. It's an old idea that I wrote up 4 years ago almost. It probably doesn't actually work that well, but a lot of these things don't work that well. Even if it works, it would just move the costs from OpEx to CapEx. But what you do is you prove that you're not mining and you get paid. And the other fun thing about this is it sort of led to some of the ideas in Lightning Network. So the idea is, in Bitcoin, the difficulty adjusts so the blocks come out every 10 minutes, right? Every 2016 blocks, you look at the timestamps, adjust the difficulty. So new miners coming in make it harder for the existing miners. So if you're a miner, you really don't want anyone else to start joining this network and mining. You really like it as it is. So if you have the first ASICs, you're good, and you don't want everyone to come in. And this is why so many people buy mining equipment and lose money, because they look at the current difficulty and they say, hey, here's this device, here's how much electricity it uses, how many coins it generates. This is profitable. I'm going to buy this thing. And what they don't realize is that by the time they actually get it, or maybe a few weeks later, the difficulty is like doubled. And now it's making half as many coins for the exact same amount of electricity. So yeah, and that's a fairly unique property of Bitcoin. That's not the case in, say, gold mining or other extractive industries. There's some kind of curve in gold mining where if you pay twice as much money to like have twice as many people dig holes and mine gold, you won't get twice as much gold. Maybe you'll only get 10% more gold, but you will get some more, right? And if you drill for oil, you pay twice as much, you'll get some more. But yeah.
And it's worse than that because you're still obligated to mine, because making 50 cents, making half as much as you were gonna make is still better than making none.
Yeah, so that happens too. So, but yeah, in Bitcoin, 2 times the mining leads to 1x the coins mined, right? There is 0 marginal product of labor in this system, which is weird and counterintuitive and like doesn't really exist in normal life. Most things most things have some kind of sublinear curve where, yeah, the first low-hanging fruit, if you're mining coal and you start in Pittsburgh and it's just sitting there on the hill and you're like, hey, that was easy. And then eventually you have to start, open pit mines and digging holes, and it's expensive and you don't get as good. But you still, if you double your effort, you're going to get some extra stuff out. Then again, there might be cases I'm sure in economics where like eventually it goes negative, where if you continue adding to members to an organization, eventually they're just like dead weight and they make it less efficient or something. But in Bitcoin, it doesn't matter how much you mine, you always get the same number of coins. So the obvious thing there is, well, we should all just stop mining, and then we'll have 0 electricity usage and we'll still get the same amount of coins.
The example is Nobel Prizes. Doesn't matter how many academics chase them, there's a unique number of Nobel Prizes.
Okay, that's another, yeah. However good the science is, you just get 1 Nobel Prize. So let's say there's 2 miners, and there's obviously more, and each mining with 2 gigawatts. And they both think, well, wait, if we both turned our mining down 5%, we'd still get the same amount of coins, but we'd be using 5% less electricity. We should have a meeting, maybe some kind of cartel. So this is sort of OPEC, right? This is a classic cartel. If we all restrict our output, we can raise prices and reduce our costs. In Bitcoin, it's like the perfect cartel environment, because if we all reduce our output, we get the same output, sort of, right? If we all turn down mining 50%, we all still get the same number of coins. The network still works fine. Maybe nobody even knows we're doing this. This is like ideal cartel scenario. Problem for cartels generally is that cartels are hard to maintain, especially when there's not a lot of trust, because there's so much profit in defecting and like going against the rules of the cartel. And OPEC has this all the time, where one of the OPEC countries says, no, we're just going to pump a bunch of oil and sell it, because everyone else reducing their output raises the prices, and now we can sell more with high prices. So in this kind of system, if all the miners said, hey, let's all turn down 50%, the one miner who then mines at full blast is going to make a lot of coins. So this is the problem. In Bitcoin, nobody trusts anyone, right? So the solution here is trustless collusion. Uh, and in the paper, it's like, well, is it collusion or cooperation? They both sort of mean the same thing, and collusion is just a bad word for cooperation. Cooperation's good. It's on Sesame Street. Everything. Okay, so the basic system is Alice pays Bob not to mine. So first the thing, Alice needs to prove that Bob can mine, because she doesn't want to pay Bob if Bob doesn't have any mining capacity that he's taking offline. She only wants to pay Bob for, having the ability to mine and then not doing it. So A posts a block header at a specified time and says, okay, B, mine for 10 seconds and give me like your 100 best shots, right? So in Bitcoin, you have this like fixed difficulty and you just say, okay, anything below this block hash is valid. But you could make one where you say, hey, give me your best 100 and I can then extrapolate or, interpolate from that what your hash rate is. And you can get pretty accurate. So they have to do some work, right? Bob does some work, but for a brief period. And I don't know, 10 seconds. You don't want latency to be an issue, so maybe 10 seconds, maybe a minute, whatever. Some small amount of work to prove that they have the capability to do the work. And they respond with that. And Alice validates it, says, okay, you've got X amount of work capacity. Alice then creates a 2 of 2 multisig transaction and sends 1 Bitcoin to this address and builds 2 transactions with Bob. This is sort of like how Lightning Network looks, Lightning channels, but this predates it by a year or 2. So the idea is you've got this funding, and then you've got 2 transactions. They're both signed by both parties and held by both parties. Although in practice, the one that pays out to Alice, Bob doesn't really need to store. He doesn't like it. And the one that pays out to Bob, Alice doesn't need to store. But the idea is they have conflicting lock times. So in the transaction header, you can have a lock time. Say, okay, this transaction is only valid after this point. So the one that pays Alice is height plus 144. So the current height of the blockchain plus 144, well, that should take about a day, right? If blocks come out every 10 minutes, 144 blocks is 1 day. For Bob, Bob gets a coin with the current lock time plus 24 hours. So in Bitcoin, you can specify either Unix time or block height. And I think everything above 500 million is a time, everything below 500 million is interpreted as a height, which means this whole system runs out in like a couple thousand years. So, this is a race, right? There's 2 transactions. One of them can be broadcast first, depending on how fast blocks come out. So if blocks come out very quickly, this will be valid first. 144 blocks, maybe it only takes 20 hours. And these 144 blocks have come out, and Alice can post this transaction and get all of her money back, get her 1 coin back. However, if blocks come out slowly, and after 24 hours only 120 blocks have come out, Bob can post this transaction first, and it will be valid and confirmed, and Bob gets the coin. So now Bob's incentives are, well, I'd like 144 blocks to take longer than 24 hours, because then I'll get this coin. And Bob has the means to influence this, right? Bob's a miner, so Bob can say, well, I'll just mine less. And if I mine such that it, in 24 hours, only 130 blocks come out, I get the coin. Cool. Right? If blocks come out fast, on the other hand, Alice gets her money back. So Alice has no real risk here that Bob will run away with the money without doing his part of the job. So Bob can slow down his mining in order to get the bounty coins. If Alice sort of estimates incorrectly how much profitability Bob has, Bob just doesn't do, Bob just keeps mining. Alice gets her money back. This collusion didn't occur at very little cost, right? Bob had to prove a little bit. There's some coordination cost, but basically nobody loses the money. So Alice can put whatever bounty she thinks is beneficial to her. Okay, I'll pay you 3 coins not to mine as much. And you can chop this up. You can have a lot of different smaller transactions and sort of make a curve a lot. If you mine a lot less, I'll pay you more, things like that. Yeah, so that's the idea behind Proof of Idle. It doesn't solve the, it feels like it might happen to some extent, long term. It feels sort of like, nuclear weapons where everyone's got them, but they don't really use them. They just sort of threaten. So it feels like mining could be that kind of thing where, well, we've all got all this mining capacity. but we just sort of threaten each other with it, and we don't really mine because the mining is actually really expensive. And it's just the threat of mining that you need. And if someone tries to do, say, a 51% attack in reorg, the existing mining infrastructure can spin up and say, oh no, you thought you were 51%, you were actually 5.1%. And we're 90% offline, and we all come back online and reorg you out. It's an interesting, I think it's kind of a fun idea. In practice, it doesn't work now because it's mostly CapEx. So this doesn't help if your main constraint is building the chips, which it sounds like it still is, like from David's talk on Monday, right? Yeah, you need to get electricity, sure, but also a really big problem is getting a supply of all these chips. And this would just exacerbate that. This would make it so that I don't even need electricity. I just get the chips. I don't really care how much I'm paying electricity because most of the time my chips sit off. I just need to occasionally prove I have them and have the ability to mine with them. So it wouldn't solve the problem of proof of work in terms of people spending tons of money on it, but it would move it towards, okay, less electricity usage, more fabrication plant usage. Is that a good thing? Is that a bad? I don't know. It might, and in certain cases, it may be that it saves people money. It may be that, like, hey, if we can collude in this way, it actually we save money, and then we can use it to build more hash power. So this might happen. I'm not as convinced. I was sort of convinced, like in 2014. I'm like, oh, I think this is going to happen. I also thought that it would become predominantly OpEx in like 2015 or 16, and it just didn't. Not even close. So who knows? But it's, I don't know, kind of fun idea. Okay, so in general, lots of new ideas out there. Proof of work does seem to work, but I think one of the big issues is it's not really compatible with the sort of Kurzweil-Roddenberry future idea. I don't know if, has anyone read like Ray Kurzweil? Like Age of Spiritual Machines. It's sort of like this future-y, like AI is going to make everything great and we're all going to live forever and computers are going to be like our best friends and we're going to take over the universe. And Gene Roddenberry of Star Trek is sort of a popular, not quite as crazy, maybe just as crazy view of that, where like we're all going to, you know, in Star Trek they don't have money. They just sort of explore the universe and make the world a better place and stuff like that. And it's like cool. And there's a lot of people who are into technology and research who are, you know, maybe not consciously, but identify with these ideas that like, yeah, we're making the world a better place. We're making computers are going to help people and it's going to be great. And I think one of the issues with Bitcoin and proof of work is it doesn't fit into that, right? It's sort of dystopian in a way. And then it's like, wait, we're going to have like giant server farms performing SHA-256 for the next 50 years? Like how does the benevolent AI fit into this system? So that's one of the reasons people, like the proof vital idea was, I was at University of Virginia and Avi Shalat, who's now at Northeastern, he was like, I hate Bitcoin because the whole point of SHA-256 is that you can't find collisions. That was the design. Like there is no, you know, collision resistant hash function. And now you've built this giant system, which the whole point of the system is to find collisions. Like, like that's the opposite of what it was supposed to be. And so it was just sort of like inelegant and ugly. And that was why I'm like, well, maybe you don't really have to mine that much. And so I wrote this thing about proof vital. But anyway, that's one of the issues that people have with proof of work. And that's, I think, one of the big you know, motivating factors for all this other research into different consensus algorithms. And further research is required, maybe. The interesting thing is a lot of the people doing proof of work are fine with it, right? So like David Monday, he's not interested in proof of stake. Despite the proof of work, you know, ecosystem being so crazy, he's just like, nope, this is what I'm doing. So none of the miners are interested. I mean, you know, miners, their job is to mine. So they're usually not interested in proof of stake. And then Bitcoin in general, a lot of it's like, no, this seems to work. We're okay with it. This is the cost we're willing to bear. But other people want to do other systems. So further research is required or not. But it's happening. There's tons of research into different consensus mechanisms. I would say in academic research, that's like the biggest thing. what I would like to see more of is more academic research in proof of work, because there's a little bit, but there's all sorts of interesting things with proof of work where it's like, oh, you know, something like proof of idle or something like the stuff that David was talking about on Monday. Like, there's not much economics research into this. And I think it's a really interesting question where you've got like, hey, I've got a device that prints money and I want to sell it to you. What? Like, how does that work in terms of economics? Like, how much should I sell it for? How much should I buy it for? Things like that. So there's a lot of new research into new proof of stake, different consensus mechanisms, economics that way. And not as much into new forms or how proof of work works, which I think is actually really interesting.